do, let's agree to replace them.
So you'll have to make do.
By the way, Ben Green will come in a couple of weeks, so I'll send a message.
So it's good that he's not here now, but incorrect. So what I want to show is basically the theorem about the fact that primes contain arithmetic progressions, but in a slightly different framework, which is the more computer science framework in a sense. So I want to basically fill in the details in the following picture, which is some vague picture that I always draw. So this is saying that the way Green and Tao prove this theorem is the kind of the following thing, that they say you want to say that the primes contain arithmetic progressions, and there is a theorem of Samredi which says that any dense subset of integers, say from 1 to n for large enough n, contains arithmetic progressions. So then what they do is they show that primes are contained in some set which is pseudo-random. So let's call this set R, and this is the set which I'll denote by Z sub n. So Z sub n in this talk is the additive group modulo n, and n is prime. Okay. So this approach which we abstracted out was it's called the dense model theorem. It says that if let's call this set primes as capital P, I don't know. So then P is dense in R. R is pseudo-random, which is something I'll explain in more detail. Then there exists some model set M, which is dense in Zn, and M looks like primes. So the notions of looks like are what I am going to make precise in the talk. And then once you have this, you say that M contains arithmetic progressions by Samredi's theorem, and hence P contains arithmetic progressions because of this appropriate meaning of this squiggle. Okay, so this is the picture we keep in mind, and let me state Samredi's theorem, which will also set up some of the notation that we'll be using in this talk. So I drew that in terms of sets, but we'll be actually talking of measures in the talk. So a measure mu is just some function, and so let's state Samredi's theorem in terms of a function like this. So suppose we have a function which is, I'll reserve the word nu for a pseudo-random measure. So let me denote this one by f. And I want to say that, so I think of the function which is identically 1 as the uniform distribution over Zn. And f is some weighted set. So let's just put it like this. On all inputs. And we know that so think of f as 1 on some set M and 0 everywhere else. Let's just complete this. No, the expectations entirely in this talk will always be over the uniform distribution on Cn. Okay, so no, I mean just once I'll write it and then I'll refer to this. But so sorry, you were saying something?
Just this is what you'll call E of f.
Yeah, this is what I'll call E of f. So let's assume that this f is a dense measure or something. It's like the characteristic function of a set which has delta n elements. Then Samredhi's theorem says that, in one version of Samredhi's theorem, that if you count the number of arithmetic progressions of length k, so they can be counted as follows. Then this is some constant which depends only on k and delta minus something which is little o of 1. And in this talk, the asymptotic notation will always be with respect to n. So little o of 1 means some subconstant function of n. It might have a super constant dependence on k and delta, but we treat k and delta as constants in the talk. Okay. So this is Samredhi's theorem. R. So x is the starting term and r is the common difference of the arithmetic progression. Okay. So what we want to do is to, we'll write the dense model theorem on that side and keep it there. So what we want to do is use the dense model theorem, which is it okay? Can you see here? So it's something which was, implicit in the proof of Green and Tau and made more explicit in the proof of Green, Tau, and Ziegler. So by now it has a lot of proofs. And sorry.
When we see k delta is just delta to the k minus 1 or something, or delta to?
No, it's much worse. It's inverse tower of exponentials in terms of k and 1 over delta. And for Gauer's proof, I think you can get Gauer's proof. You can get 3 length tower.
Okay. I thought that this tower only appears in the little of one term, and once you go above that, it's like delta to the k.
But nobody knows, right? Like for fourth term, progressions, I think nobody has any idea.
Okay, so the dense model theorem says the following, that you have a function f which is which is bounded, or sort of is a subset of some set given by a measure mu, which we think of as pseudo-random. You have a family of tests.
So we think of this mu as mostly 0.
It's mostly 0, yes. So think of f as the primes, as the characteristic or some weighted function of the primes, and mu is maybe a slightly larger set, but still very small density. And we have some class of test functions t, and we want to come up with something like a dense model which looks like f with respect to t. So t is a collection of functions, and what I want is for every function in this class, the correlation with so I want some function which describes my model set, with this property, and also I want that this function should be dense. So I want the function to have this property. Okay, this is the conclusion I want in the theorem.
First expectation is from over nu, and the second one is
No, all expectations are over z. Z. Everything is over z. Yeah.
And you want E of FM to be delta.
I want E of fm to be delta So the condition I'll put is that the identity function is in T. So I can take G to be 1 here. So I'll get that E of Fm is close to E of F. And I'll assume that E of F is greater than or equal to delta.
E of F, but we thought E of F is almost 0.
Yeah, but F is not bounded. F is not between 0 and 1. F is between 0 and nu. So for primes, we can think of the measure, which is so let's think of F as the following. It's the von Mangold function. So it's like log n on primes. So then E of F can be large.
So it's not normal.
It's not normalized to be between 0 and 1.
So in what sense is a new pseudo-random?
Yeah, that I'll explain in a minute. So right now I haven't written that. Yeah. Yeah, yes.
So mu only appears once. Can you write the statement explicitly?
Yeah, I haven't written the statement yet. This is just the conclusion I want. I haven't written what is the hypothesis.
So for the above ones, it's for every f, mu, and t.
For every f, nu, and t, yes. And they are all functions which take positive values. Okay. So what I want is that nu should be indistinguishable from the function which is always 1, which I think of as the uniform distribution over Zn, with respect to tests in some larger class, which I have written as T to the 1 over epsilon square. So what is this class? This class is the set of functions which can be obtained by combining 1 over epsilon square functions in T. So it's a function. So in fact, I mean, for what we'll need, T1 over epsilon square will be very simple. It will be of the following form. It will be close to some polynomial of degree 1 over epsilon square, or say.
Just 1 second. What is the assumption for every G prime in this bigger class?
Yes.
What do we have?
This nu looks indistinguishable from the function which is always 1. So expectation of G prime x is close to the expectation of G prime x nu x. Okay.
That's big O of epsilon delta.
Yeah. So this delta is what we have in the assumption here. And so this, what we'll need is something very simple. It looks at the sum of 1 over epsilon square functions from T and just computes a low degree polynomial of the sum, of the entire sum. I mean, different proofs give you different definitions of T to the 1 over epsilon square. So in the proof of Green-Tau and Ziegler, instead of 1 over epsilon square, you had 2 to the 1 over epsilon square here. It was a function of 2 to the 1 over epsilon square functions. Then in the later proofs so one proof Russell will show next time, and then there were some other proofs by Omar Reingold, Luca Trevisan, Salil Vadan, and myself, and there were a couple of proofs. They can give you a function of 1 over epsilon square. It's actually a step function, so it looks at the sum of few of these g's, and then is a threshold function. If it's 1 if the sum is larger than a certain quantity and 0 otherwise, but a threshold function can be well approximated by a polynomial, and we'll just think of a polynomial.
Why can't you set f and m to be just f?
Why can't I set fm to be just f? Because this condition is not satisfied. Fm is between 0 and 1 and still has expectation bigger than delta, so it's very dense.
So where would you write that FM has expectation?
Because I can take g to be 1.
And F can be larger than 1? Is that the problem?
Yeah, f can be larger than 1. For example, for primes, this is what we think of as f.
So, I mean, I guess for us will be maybe more natural to think of f as bounded. If you think of the normalized f where you divide something so it's at most 1, then you'll have to just multiply when you take the other expectations. Where
Yeah, so one.
you and the f, you'll just be scaled with an appropriate factor. And you'll think of them as basically as expectation, not over the entire set, but only
But over some restricted distribution, yeah.
First to think of the normalization so that the expectation in the uniform distribution is about constant for all the functions discussed. And the hard thing will be to put another infinity.
I mean, this way I won't have to worry about what I'm taking expectations over.
To
And
some
that's it.
extent, when f is large, it's like, I guess, which is somewhat confusing. We just have to understand that you're really talking about a small set.
Yeah.
Yes,
So
and
small set, and you just
a measure of
compensate by
a small
giving
set.
its big value.
Yes.
When M is a set, you want to think of nu as being 1 on the set and 0 everywhere else, right?
Nu and m are slightly different.
What
Nu,
about the
When
density
you
of the
think
set?
of nu as being a pseudorandom set, distribution of the set,
yeah.
then nu is bounded by 1, right?
No, so let's put it like that's.
What about the density of the set? Will be larger than 1 on the set and 0 else.
1 over the...
Let's do it. So let's talk of nu, and f is defined as uniform over primes, right? Between 1 and n. Right. So now I was taking f to be this for primes between 1 and n.
You have to define it.
Yes, at some point.
Okay, yeah, so I should do it.
Forget primes, it's any set. How
Okay, let's take any small set. Okay, so let's call this set S. Now, I want nu to be bigger than f, and I want nu to be pseudorandom. So, say S is contained in T, I take nu to be if you want to think of it as a probability distribution. If you want to that. Okay. Okay, yeah.
The expectation of nu should be 1.
Yes.
So if it's uniform over some subset, you scale it. It's larger than 1, so the expectation will be 1.
This is what you could think of as. So the expectation of f is not 1. The expectation of f is delta.
I know for T. Okay. Right.
Expectation of f is just delta. If s is a delta fraction of t. Now I just normalize them so that the expectation of nu is 1. The expectation of f is whatever the size of s over size of t is. But they are not bounded between 0 and 1. They can be large.
There we don't need expectation of mu is 1.
We don't need we do need, because again I can plug in g prime to be 1.
You can take this.
And that says that the expectation of nu should be very close to 1. Okay, so now for the rest of the talk, what I want to just see is how to define this class of tests and how to prove the required hypothesis and derive the conclusion from this. Okay. So the most natural class, what we want to look at.
Maybe, I mean, at some point you were going to define that, or that can wait till later.
Lambda thing?
Yes.
Well, I mean, I can define it, but I'll not use it for a while. So, but
So for now, think about it as about log n.
I mean, it's
Like log n prime and 0 and 0 or something
Yeah, it's exactly basically if n is equal to some power of a prime, then you take it to be log p and 0 otherwise. So this is not what we'll actually use as f. We'll use slightly modified version, but it will come from this. Okay, now so if you wanted to look at this function and see what class of tests is natural, so we want to again look at this expression. In terms of f, which is like that or coming from the primes. So it's not bounded between 0 and 1, but it's some other expression. And we want to look at this expression and say that this is large, like it is in case of actually dense sets. Okay. So here is a candidate G. Sorry, no, I omitted fx. So this is G. So the expectation, so this, when I look at this expression, this is nothing but the expectation over x of f of x, g of x. Right, if I take G to be this. So, I'm sorry? G is a function of x. Yeah. So, that's the candidate I would like to take. Now, what does this mean? So, I can't choose G exactly depending on this f. I want G as a class. So, let's I'll actually look at a slightly different G of the following. So, I haven't tried very hard, but I don't know of how to prove all the things required with this notion of G. I'll use a slightly different G, which is the following, and I'll say why it's nicer. So I'll define the family in a minute, but I'll just want to define G as in terms of f right now, and I'll get to the family in a minute. Sorry? Okay, sure. I mean, yeah, there will be some k minus 1s showing up. If you don't like them, we can just do length k progressions. Well, we can look at length k progressions. It's fine. So what is this expression? So omega 1, sort of omega is just a bit string of length k, and omega dot h means that I look at k elements of the group Zn, and then I write down the sum of the ones which correspond to non-zero bits in omega. I have omitted the omega, which is all 0 strings, so there is no f of x. The nice thing about this G is that f of x, g of x is something well known, whose properties are understood. And this is what is called the Gower's norm, or the kth Gower's norm of f to the power 2 to the k. So the nice thing about defining G like this is when we manipulate them, we can use all properties of a norm that are available here, which are not directly available in this setting. Okay. So our family of distinguishers will be the following.
So you will prove that this expectation even is large.
I will get from the theorem that this expectation is large by using a class of tests which gives me. And using this expectation, I'll deduce that this expectation is large. So I'll have to show that this suffices. So this class of tests does depend on the measure nu which I have in mind, which is the pseudorandom measure. But that's okay, because in the hypothesis of the theorem, both nu and the class of tests are given. As long as this condition is satisfied, I can use any class of tests. It might depend on nu.
So you're allowing an arbitrary function f.
Yes.
IF can be negative. Why did you write absolute value?
I will actually have to look at functions of the form which are some f prime minus something which is between 0 and 1. So this is the cleanest way to do it.
So it will be actually from minus 1 till nu, or something like that. Or
I'm sorry?
okay, sorry. Yeah, for minus 1 till nu plus 1, that's the range that.
Yes. Minus 1 to nu actually even. It will not go to slightly bigger than nu. But this is just a uniform bound on all values. When nu is 0 also this holds. Okay, so this will be the class of tests. Now we need to show that this class of tests is sufficient, and also that nu, there is some nu which satisfies the required condition of the theorem for this class of tests. Okay. Okay, so sorry.
So f, what this is saying is, like, on the almost primes,
Mm-hmm.
f could be up to, the fraction of almost
Yes,
primes, right?
yes.
But when x is not an almost prime, f is basically bounded between -1 and 1. So there's sort of some mixture of the uniform distribution.
It's
and
between also just between -1 and 0, not even.
-1 and 0.
Yes.
Okay. So it's like some difference between a distribution on almost primes
Mm-hmm.
and a distribution on the uniform distribution.
A dense distribution.
Dense
Yes.
distribution.
Yes. So, I mean, I'll just show in a minute what kind of things this applies to. So let's just denote this by to sort of show that it depends on the measure nu. So now I need to prove two things. One, the dense model theorem. And the second one, which is simpler and will show first, is that so what did we call the function given by the dense f sub r? Okay.
So the characteristic function of nu is not in this set? What?
The characteristic function of
Nu
nu
itself is not in this set?
nu itself is
It is. This is at most nu plus 1.
Well, no,
oh,
Well, okay, we
no,
did.
the Gowers, this kind of Gowers norm of mu is it?
Yeah, the Gauss.
yeah, the function defined like this.
Okay, because because if nu itself was in the set, that would not work, right? Because the expectation of mu squared is very far from the expectation of.
So it's something which, when combined with nu, will give the Gowers norm of Gowers norm to the 2k of nu.
So that would become like something very.
Yeah. So these functions are, in short, called dual functions or Gowers dual functions. Basically, because when you take the product with f, you get that Gowers norm. Whatever was there about f. So one thing we need to show is this. Second is that if we have fm from the dense model theorem, then what we get from the dense model theorem, which is that so we need to deduce, if we from the conclusion of the dense model theorem, that set f, set defined by f, which is the primes, has large arithmetic progressions.
You need to go both ways between these arithmetic regressions and the Gowers norm. Right? So
I
you
need
say-
to go both ways? No,
Yeah, so
only one way, right?
So from this, you know, like the Gowers norm. Sorry, from Zemaretti's theorem,
Mm-hmm.
you know that fm has many arithmetic progressions.
Yes.
The right number.
Yeah.
And then from that, you have to deduce that his Gowers norm is high, which means that f's Gowers norm is high, which means then you have to deduce from that that the arithmetic progressions are large.
No, I don't have
Are
to.
we proving Zemaretti's theorem?
No, we are not proving Zemaretti's theorem. We are using Zemaretti's theorem to give progressions in primes.
Right.
Or using
Zemaretti's theorem gives progressions in actual dense sets of subsets of integers. We are not going to prove it.
So
That will take longer than 2
but
hours.
I mean, I guess what I'm asking about what happens in like set number two, because you're gonna use the Zemaretti's theorem.
Yeah, so I'll show step 2 right now.
So step 2 is the basically Cauchy-Schwarz.
Uh,
Well, okay.
sort of, I mean, yeah, basically Cauchy-Schwarz, but slightly tricky one. But that's all.
Something I guess non-intuitive about T nu is, I mean, I guess the fact that it depends on this
New.
Because somehow, like, our intuition is that usually you think of pseudo-anonymous with respect to simple functions, and you think of this new as something that complex, that these things cannot approximate, but here these things can depend on it, and they look like you start by taking the characteristic function of nu that is already the best distinguisher, and you make it even more complicated, and somehow you make it weaker in the process.
Not the characteristic function, but some dual function, right? Whatever comes from the Gauss.
Yeah, what I mean is that
Yeah.
this dual somehow becomes, instead of being even more powerful, becomes less powerful to some extent.
Why?
I mean, the best distinguisher for nu is the characteristic function of nu, right?
Right. So this is exactly the point, right?
These
So
functions are even more complicated than that, so somehow.
But
so there is an independence which comes in. So here's so if I looked at expectation of nu of x minus expectation of nu of x square, which is exactly plugging in the distinguisher between 1 and nu as nu itself, then this will be large. This is not bounded. But if I looked at the distinguisher as an as the following: nu of x times nu of x plus y. So the distinguisher is whatever you would get by looking at the dual in Gauer's one norm, which is just a shift, right? Now this is very close to 1, because the input you are testing on has some independence from the original input on which you are running your original function. The same is true in Gauer's norm. There is an x which is not included here, and the rest of the inputs on which you compute the function nu have some added term. So there is some amount of independence there, which lets you still have pseudo randomness because they're not testing on exactly the same input. So this will be this would come if we were looking at the Gauer's one norm or looking at arithmetic progressions of length 2, which won't make sense, but this is the expression we get.
is the restriction up to nu really necessary, or is it just because you want to? I mean, does that really make this class weaker, or is that are these the strongest members of the general class? Let's say if you remove the restriction that f is
It just
bounded.
says that your set is a
If I say
subset
f
of
is-
the pseudo-random set, more or less, right? That just says that your set that you want, like the prime, is a subset of the pseudo-random set. No.
If I remove that restriction, then I could have functions which test on one single input, or which are even more restricted. There I can't hope to do much, because they will tell apart nu from the uniform distribution.
It's completely analogous to saying that Fm is less than 1. It means that M, the dense model, is a subset of the whole universe. In the same sense, the primes are a subset of the pseudo-primes. It's just it's just containment. Right?
So suppose we have the conclusion of the dense model theorem. So we know this. And now we want to deduce something about progressions in F. So what we know is that the expectation, or the inner product of F minus Fm with G is less than epsilon. This is just the same as the expectation, right? For all G. Now let's take the dual of this function f minus fm, which is where we'll need the nu plus 1. Then this inner product is nothing but the Gauer's norm and this is in T by assumption, by just because this in absolute value is at most nu plus 1. Okay. So, this just says that the Gauer's norm of f minus f of m is small.
That's the only thing you'll use.
That's the only thing I'll use. How to prove that will require, sorry?
No, in the from your assumption that for every g you have this.
Yeah, so I actually just use this one g.
For this function.
Yeah, just for this g. And so this is one thing that I'll prove later. Now suppose I can prove one more theorem which says that if I look at different functions, not the same function. And so if I can prove that the expectation of this product is no larger than the Gauer's norm of the function with the smallest Gauer's norm without the 2 to the k in this collection, then I would be done if I could prove those. No, I don't want the 2 to the k here. I can't prove it. I'll just prove it without the 2 to the k. So then I'd be done because I'm looking at the following expectation. Each f I can break into 2 terms, and so this I can write as a sum of different products.
You wanted fm though. F is fm plus.
So I can just f. Now, each term of this contains at least one function of this form, all but one terms. Right. So this is greater than equal to.
So you just broke every function like this.
I just broke every function, and then I look at the subset S where I took fm and the subset where I looked at f minus fm, right? So each will be a product of this kind. So I just look at one term from this in which I am looking at the set S, which is the whole thing. Sorry? Yeah, just the Gauer's norm, or the this is the term where I took all fm's, and the other expressions contained at least one function of the form f minus fm. So I can bound the expectation by the Gowers norm of f minus fm. So I get this.
This is like epsilon to the 1 over 2 to the k.
This is epsilon to the 1 over 2 to the k. This is ck delta by Samredhi's theorem. So if epsilon is small enough, this will be negligible. So the two theorems I want to prove are this and this.
So the theorem you would prove would be in absolute values.
The theorem I would prove would be in absolute values. Is the constant? Well, it will depend on k. It will depend on k. Okay. I'll write this in again. Okay, so now let me describe to you a little bit about what is the nu that they look at and what is the f that they consider the paper.
So just the theorem 2 is what we I guess know, like similar in what we know in like multi-party communication complexity. This is like this iterated Cauchy-Schwarz.
Yeah, it's an iterated Cauchy-Schwarz. And I mean, we'll reduce these two from some things we know about nu, which I'll write in a minute, which follows from estimates of Golden and Yilstrom. I will not show those estimates, but I'll write down what they deduce. Okay, so to begin with, the first attempt at taking f.
So now you're doing 1, right?
No, right now I'm defining nu before I prove either of these. So I can write down what nu is, what it looks like, what we know about it, and then we can maybe take a 5-minute break and then I'll prove 1 and 2. So we would like to take f as this, which is a natural measure to get the primes, which I'll remind you is this doesn't directly work because it's hard to come up with a mu or a nu which has this property and is still pseudo-random, because sort of this function is not well distributed in sort of arithmetic progressions in terms of small primes or factors of small primes. So it avoids or residue classes of small primes, to be more precise. So what we do look at is
claiming that it's impossible to find a mu that works with this f.
yeah, I mean, with the correct pseudo-randomness properties, if you want those pseudo-randomness properties, this is too unevenly distributed to get that, and you cannot get a nu larger than this. So
You need to decrease it, right? You have to decrease it. You cannot increase it. Whatever you take, you cannot take. Because you are looking for your arithmetic progression in the prime.
yeah. So I'll look at something smaller than this. But as long as it's nicely distributed, that's fine.
What's the counterexample?
I don't
You
know
have
of
to
an
know what
explicit.
mu is. You have to
I mean,
question to answer. You have to understand what mu is.
No, you can
Clearly
show a
there's no,
distinguisher.
there's no new, right?
No, you can show a distinguisher
Yeah.
without knowing nu that somehow demonstrate that f has small. You don't really have to know nu, right? You can show some distinguisher that shows that f has small size that somehow.
Or maybe, yeah.
I mean, I don't know of an explicit counterexample. I'll write in a minute what this is. Think of so it's the product of all primes which are smaller than log n or some nicely growing function of n which doesn't grow too fast.
Log of what? Wn plus 1.
Yeah, I'll just say in a minute.
So,
What is the input to n? N?
Yes. So f of n actually depends on the log of wn plus 1, which is some larger number.
W times n?
so you take log n, you take all the primes smaller than that, and you multiply to get w.
You look, say that again?
So you're given input as n.
Yes.
You look at all. You take the product of all primes that are.
No, this is capital N. This is capital N, which is just fixed.
Okay,
Oh, it's fixed.
Yeah, yeah.
so W.
We are always working in Zn. W is a fixed number. It has nothing to do with n.
But w is fixed.
So now I'm confused. This is W times n?
This is W times n, yes. W is not a function. W is a number which depends only on capital N.
What is not W? What is the symbol?
Oh, this is, yeah, I'll say. This is the number of numbers co-prime to W, or the totient function. So W is just a product of few primes, and the totient function is just p minus 1, a product of p minus 1s for all those.
Of the,
Yeah.
So in other words, you're thinking of the set R as those without a factor, those numbers without a factor less than log n, which means that they're exactly those that are co-prime to W. And so this phi of W over W is the normalizing.
This is a normal, yeah.
Normalizing scale so that we're within that distribution. And then you're really just looking at those primes that happen to be 1 mod W within that set, something like that.
Yeah. So this does two things. One, we have removed the weight from prime powers. This is only, I mean, think of n, if wn plus 1, wn n1 plus 1, wn2 plus 1, and wn3 plus 1 are in arithmetic progression, then n1, n2, n3 are in arithmetic progression, and vice versa. So if we have an arithmetic progression in this set, we get an arithmetic progression in this set. Now, this set, the set of wn plus 1 numbers which look like wn plus 1, contains only primes. So one thing we have done is removed all prime powers. The second thing we have done is restricted ourselves to a residue class of w, where w is a product of large primes. And this is nicely distributed if you look at a residue class of a smaller prime. So I think that's Dirichlet's theorem, or, yeah, which says that if you look at any other small prime, then they are roughly equidistributed within the residue classes of a smaller prime. This somehow turns out to be more helpful in constructing a pseudo-random measure.
So the pseudo-random measure will be what Arthur said. There will be all the numbers that are one mod. It will be just an arithmetic progression of numbers which have no small prime divisors.
It's slightly more complex. I mean, I don't know how to interpret it like that.
But anyway, it's easy to see that this function is smaller than the original, right?
Smaller as in up to the normalization, if you forget. But yeah, it has a smaller, it's zero and non-zero on a smaller set.
That's right. It's non-zero on a smaller set, and on this set where it's non-zero, it's smaller than the value it would take in a.
I mean, it's kind of confusing because.
Well, that's not clear, right? That would be f of that would be log n. Yeah.
I mean, I mean, maybe, I guess it would be maybe more intuitive if you write it as f of wn plus 1,
But I want this to take this value at n, right? Yeah, so what we have done is shifted the primes. Like now we'll look at the progression in terms of these numbers, where f is non-zero. Those numbers are not prime. If you look at w times that number plus 1, that's a prime. So but if you find a progression here, you'll get a progression here. That's all. Yeah.
I just wanted you to again explain what's the advantage of this f over the previous f.
So I mean, this is something I don't understand very clearly, so I can't explain very clearly. But one problem with this f which prevents you from getting nice pseudo-random distributions is that this f does not have good distribution when you look at residue classes of small primes, or how it behaves modulo small primes. This one has a nicer distribution because you have restricted yourself to a large residue class, a residue class of W, which is a product of a lot of small primes. How exactly this fact helps, I don't quite understand, because I don't understand those numbers in the estimates that will come up. I'll just state them. And what I wanted to do was just show this and then show the proof. I do not know the details of that.
Simple question. Why
Yeah.
why is the normalization this way and not the other way now? Should it not be W over 5W?
Should it not be W over? No, because this log n is already there, right? So
I mean, it would be non-zero over 5W elements.
no, so f of n otherwise would have been log n.
Yes.
When you now I've increased it.
Yes.
You are.
I've increased it, right? Instead of log n, I'm writing log of wn plus 1. If I was just looking at this function, f of n would have been log n. Now this is something bigger than log n.
I see. You increased it because you really want that it will be a delta function of your pseudo-random set.
So
You're taking less now.
what I knew for this function, which is coming here, this is close to 1. That's the prime number theorem. And what I want also for this, that this is order 1, right? So this normalized factor looks right because it's less than 1 and it compensates for the increase here. In that sense, it's the right order of magnitude.
You just showed that it's less than 1, but
No, it's a Dirichlet theorem. You need to use it. You need to know that the fraction of primes in an arithmetic progression is, what you expect. So only for, jumps, only from starting points which are relatively prime to W, you'll get.
I mean, you can avoid Dirichlet's theorem in the way that you can look at classes here. There are different R's which are coprime to W, and one of them will work because when you look at the average over them, you get 1. So because then it just becomes close to this, and then so for some R it will work. Dirichlet's theorem basically says that for every R it will work. So that's an added benefit. You can use 1, but you can use some R without getting to Dirichlet's theorem. Yeah.
The purpose of the log n is to be larger than some function.
It's something which grows to infinity. I just wrote log n for concreteness. You can use anyone here. Okay, just to say what nu of n looks like. Choose some large number. something, and then I'll explain in a moment what I mean. So I guess I'm defining too many functions, but something, but when Wn plus 1 is a prime. So nu of n is some function which basically comes from Golden and Ljungström. So these are normalization constants. What you basically do is that you look at lambda of n, which can be written as mu of n log of n over d, and you truncate this sum at r. So you don't look at mu of d.
Mu of n is the mental sum.
So this is d divides n. So mu of d is what is called the Mobius function, which is just the parity of how many primes are there in the product if it's square free. And lambda r is when you truncate this sum at d which are no bigger than some number r. For that you can prove the right kind of, so you can prove two estimates for that which will suffice for the pseudo randomness. This was considered by Golden and Ljungström.
Didn't we want mu to be a distribution over almost primes?
A measure or sort of some weighted function over.
You're requiring the condition that Wn plus 1 is a prime. It's still a distribution.
But nu is over n. It's
No, but it is saying.
No, nu being over n is just a folding of the function.
no, actually, you're right. So this is slightly different. Sorry. So it's actually non-zero over some interval of this size, where gamma is a number which depends on k, and it looks like something like 1 over k factorial.
So the divided condition on lambda r,
Sorry?
you have d less than or equal to r,
D less than equal to r, and d divides n still.
and then you need an n on the left hand side too.
Then I need,
It's lambda r of n.
oh yeah, I'm sorry.
Why is f less than nu?
Sorry?
Why is f less than nu?
F is not exactly less than nu, it's less than some constant times nu, some number which depends on k. Within this range again, not always, but only within this range. So we'll actually take f to be this when Wn plus 1 n Wn plus 1 is prime and n is in that range and 0 otherwise. So within this range, it has a weight which depends on this number, and this weight is higher on primes and smaller on non-primes. That's why you get almost primes, because it's a weighted distribution. But you're right that I write down this distribution over all numbers, not just when Wn plus 1 is a prime. Look, I mean, okay, so
Just in the case that we have, just to see this P of n for the case that R itself, R will be fixed, right?
R will be fixed. It's something depending on n.
Some power of n.
Yeah, small power. Yes.
Okay, it's fixed. And then what happens when Wn plus 1 is a prime? Then what do we expect to get there? So for some prime, what will be? Why would this be higher on prime?
Let's just check, right? So
I mean, this is a sum over everything that divides n, right? So
Um,
it's bigger
so-
when
All of
you
it
have
is
more divisions.
truncated.
No?
It's truncated.
right, but
So when n is prime, there's just one term in the sum. D equals 1.
Yeah, that's right.
yeah, but when
Then
Wn
log
plus
R
1 is
is
prime.
normalized by log R, that's why the square is like that, right?
Yeah.
So but if it's a product of two primes,
Yeah, but still, like I mean, if you sum a lot of like random things,
Oh, I
they
see, I see.
go like
now the log is small. Well, yeah, it's hard to say why it's exactly a good choice, but I guess
No,
they
but
know how
why-
to prove it. No, but one can tell that it, you know, that
Why is
it's
it
not-
higher on primes than non-primes?
Because this will be a small, so you'll get log of the factors, right? You'll get a factor 1/4. It's a small, I mean, you'll get, what will you get?
What is R? R is like it's like this small power of.
But anyway, it will be divided by D. It will be divided by this divisor of n.
So say that n has a small factor, okay, then you can sort of pair up the terms, those that contain that small factor and those that don't. Okay, and the Mobius function will alternate between those pairs, and the log R over it'll be log R over something and log R over something just a little bit bigger, and they'll almost cancel out. I guess that's the idea.
So if n is a prime, then let's say the only thing you get there is one number, which is something like log r.
Yes.
Right? When it has two prime factors, you get something like log r minus log r over p1 minus log r over p2.
No, because
plus?
only one of them is going to be small.
Okay, only because only one of them is going to be small.
So
If it has two prime factors, one of them is bigger than.
if n is only
No,
three
Russell.
prime factors, then
No, r depends on capital N, and I'm talking about little n, which is two prime. Both of them can be small.
What is R?
No. R is much smaller than small n because n is like a constant times n, and R is like small power.
Right. So R is much smaller than n.
Yes.
So
N has
so
no
you're
restrictions.
only looking at
Okay.
those p's that
No,
you're
but
only looking at those
gamma
p's.
will be much smaller than log base n of R. Gamma will be even smaller, right?
No, gamma.
No, gamma is a
larger than
constant.
R, right?
Yeah, it's constant.
Gamma times n
Oh,
is
okay,
larger than
you're
R.
right.
I see.
Okay, it's
So
constant.
if
You're
n-
right.
If n has only prime factors, if all prime factors are bigger than R, right,
Yes.
then there still is only one term.
If all prime factors are bigger than.
R, there's
Okay, yeah, then there is still one term. Yeah.
right, and it's the same value. It's also log R.
Mm-hmm.
So anything that's prime or has only big factors
Yeah.
is contributing this log R.
Yeah,
Okay,
that's
so it's
right.
constant on those numbers, and then we want to say anything that's not essentially, that has several small factors is contributing something close to 0.
Yeah, which
Much
is
smaller.
much smaller.
But why is it all in minus sign and not in plus sign like the other contribution?
because
It
the
alternates.
They're different signs,
the
but
Möbius function
The Mobius function alternates in signs depending on the number of factors.
mu of d will depend on how many prime factors d contains, and it will alternate. So the signs will be different. I don't care what is plus, what is minus.
Okay, so it's plus, minus, but
Yeah.
dominant term is the first one.
Yeah.
So,
Well,
so
the sum of the Mobius function of the divisors of the number is 0 unless you're 1. So you get cancellation when you sum the Mobius function. I mean,
But if we're truncating it,
Yeah, it's
but then that's like considering the function of, product of those small guys.
yeah.
So
So maybe we were, but you could have cheated us from the beginning and just told us that the f is a von Mangold function, and nu is just a normalized distribution on the almost primes. Okay.
Could
and
be,
it
yeah.
has these bounds, right? I mean, we are just going to state bounds about this.
I just will state what our bounds
we
are known.
might as well. What?
I mean, it's not necessarily true. I mean,
No, it's probably not true. I'm just saying, so there are details there that are, we are anyway going to take a black box, so it doesn't matter what, what we call. Might as well imagine that these are primes, from Mangold function, which is supported on primes, and the other one, which is a complicated mu, is just supported and normalized over almost primes. And they prove the bound on it, and the exact definition of this pseudo-random set or measure is more complicated than you might think.
yeah, the problem is with this that the problem is that this almost becomes equivalent to taking the entire step 1 as a black box, and the step 1 is like very
No, but if
because
they prove
it
the
depends
bound,
on
but
the
if
mu.
they prove the bound on the original, on the original set, on the natural set of almost primes, what would you do? I mean, the proof you are not going to see.
Yes, but somehow I wonder if some participants will see how is it okay that t depends on nu and you can still satisfy the hypothesis, or maybe that's buried inside the math and you won't be able to see it. But,
Well, I mean, it will be clear in terms of the conditions that I'll state or the bounds that they know on this nu, why they imply this, but why those bounds are true, I will not show.
Yeah, okay, so go on.
Okay, so don't look at that word. But, so there are two bounds that they derive, which almost give you what you want. Is one is that when you look at linear functions in terms of few variables, so phi is a linear function of t variables.
It's not the previous.
Phi, okay, let's just call it something else. Let's call it n. So it's some other number. So it's just some affine function, and you are looking at the product of such linear functions. Say R of them. So the expectation of product of linear functions is close to 1 as long as these linear functions are independent in the sense that the linear part of any of these two functions is not a constant multiple of each other.
Or is that you don't need a rank?
You don't need a constraint on the rank, just that they are not multiples of each other.
Right. You don't get.
You don't, so when you think of,
Twice.
yeah, because when you think of what linear expressions arise in Gauer's norm, they are a dependent set. They are not all independent linear expressions, but no two of them are multiples of each other. And so this is what you are saying. When you will look at nu times a distinguisher or something coming from T, that will have no, nu just has one variable x, and the elements in T have a sum of few elements, none of which is just x, the other things. And this condition guarantees you that this product will be close to 1. So this is one condition. The other is a condition which is says what happens. So this is an expectation over x1 to x t. The other is a condition which gives you some handle on an expectation of products like this when there are terms in which the linear part does look the same. So now you have expectation over x nu of x plus b1 nu of x plus br is less than equal to okay. So when you just have x and then there are some other terms which are different, then you can bound this expectation using some function of the distances between between these terms. The only condition you need is that this function has bounded moments. So a moment of this function depends only on t, does not depend on n. This function tau, n, capital N. It just depends on what moment you are looking at. But so these are, I mean, and there are some conditions about how many of these terms you can take. We can think of them as like 2 to the k or k times 2 to the k, where k is the length of the progression or k plus 1 is the length of the progression. And then there are more conditions about how large can the coefficients be, but we'll ignore that.
So who proved this?
This they deduce in the paper from Golden and Ustream. So yeah, and probably not in the same form, but they deduced it in the Green Tau paper from them.
So this already says like these are like things that in particular mean that nu is not an interval.
Nu is
almost primes are not like an interval, right? Because that would be very wrong in interval. I guess if it was like you had an interval of fraction like the first n over log n numbers, and you would give log n on those and 0 otherwise, then that would be very that would go to infinity.
The second one, you mean?
Both of them.
Both of them.
Right. I mean, if L1 is x and L2 is
x1 plus x2.
X plus 2 or x plus 1, or I guess the second one definitely.
The second one does. I don't know about that.
Maybe you'll have two nonlinear terms, so it will be. The second one, yeah. So the first one, is it like, does it use special properties of mu?
It does. I mean,
So what? So I mean, it's trivial to see that that if it was an interval, then the first one will be wrong also.
well, I don't know actually. If you had just a uniform distribution over an interval,
The second one would be false because the nu of x times nu of x plus 1 would be something like log n and not 2.
it's the expectation over.
It It would be
And-
like, suppose it was like the uniform of the interval would be something that is log n on the first n over log n things and 0 elsewhere.
Ah.
So nu of x times nu of x plus 1 would be something like,
If it's a small interval, you mean it's an interval of size n over log n, and you have weight log n over,
yes.
you have weight log n on all the elements.
Yes.
Yeah, so then it will be log n.
Right, the second one. So the
The
first
second one.
one would be also, is it easier to see that?
Well, probably if you look at, I mean, not just two functions, but if you look at four functions which form they form a box-like structure, then will you get it with the Gowers now? Then you'll probably get it. Yeah.
So you want to say that these hold for some linear functions?
No, for all linear functions with bounded coefficients. So theCij's are bounded by something like k. But for all linear functions, when the linear part is not the same for two of these functions, or not constant multiple, then this holds for. So it's a very strong property. It just fools all products of R linear
And
tests.
you don't have any summation saying that the sum of the coefficients is 1 or something like that?
The coefficients are bounded. Each of the coefficient is
I mean,
bounded.
bounded is okay, but I'm just thinking that if you just scaled all the linear functions, then it would change. Oh, nu is just measuring whether you are in the set or not. So
Some weighted
right.
measure.
This is saying that if you look at some linear functions, then you okay.
The
And
linear
these-
functions will be what comes from the Gauss norm, will be just the shift. So
Right.
So we'll just see what the linear functions are like when we try
And
to
the
prove
BIs
those.
in the two statements are not the same.
The BIs in the two statements
second one
need
says
not.
you-
I mean, this is just some for all B1 to BR. This holds,
You pick it.
and this for all Cij's and BI's. This holds. Okay, so now if I want to prove the second condition, which is a little simpler to prove, so we can do that first and just see how we apply these, and then we'll prove the first one. So let's prove the second condition, but with k equals 2. So we are looking at progressions of length 3 or product of 3 terms.
what do we assume about the F5? The F5s
Um,
are not new. They are all each is not new or new plus 1 or something.
Yeah, so what we'll assume is that
you were right, the Gauss cube, also if nu was an interval, then 1 would be large also.
okay, so thanks. Done. So let's just look at the following. So I have rewritten x plus r, x plus 2r in terms of x, y, and 2y minus x. And let's just show that this is less than equal to the Gowers norm of the same proof essentially holds for larger k and other the minimum part. So I mean, it's basically just Cauchy-Schwarz. So all you do is so this is an expectation over x and y. So you write this as an expectation over x. So we can bound the norm of f0 of x by nu plus 1. So just bounded by the absolute values. And then you apply Cauchy-Schwarz, where you split up this nu plus 1 as and then you apply Cauchy-Schwarz on this part and leave out the nu plus 1. So sorry, this is not square. Okay, sorry. Times so
This is 1, right? The integral of
about 2, because I have nu plus 1. So I have power half of this times about 2 to the 1 half, because the integral of nu plus 1 and the expectation of nu plus 1 is about 2. And then this is you can write this as expectation over x, expectation over y and y prime of f1y, f2 2y minus x, f1y prime, f2 2y prime minus x, nu plus 1 of x. And then you do the same trick again. So what you end up with is what is exactly like Gauer's norm up to a small multiple. So basically you do, now you bound f1 by nu plus 1 and you apply Cauchy-Schwarz again, and what you get at the end is expectation of x, x prime, y, y prime, f2 of 2y minus x, f2 of 2y. So this whole thing to the 1/4 times some factors which are like
Why did you get, here you got just 1 nu and there you got 4? Maybe here you need,
no, here I'll get 1, that is fine.
how do you get 4 afterwards?
How do I get 4? So these will give me 1 nu each when I, and this will square up. So I'll get square x prime, x and x prime from this, and a y from this and a y prime from this. So that will be 4. Okay. But some expression that looks like this. Now this is a cube. So 2y minus x plus 2y prime minus x prime is equal to 2y minus x prime and 2y prime minus x. So I can reparameterize this in terms of x, h1 and h2. And so what I'll get is something which looks like this. This I cannot express in terms of 3 variables. This will need a 4th variable, right? These are 4 independent things, x, y, x prime. So let me just write a 4th variable, which is say y, and some function, some weight function, which can be written in terms of x, y, h1 and h2. So I'll take a linear transformation of this x, y, x prime, y prime to get some other function. So it's almost like the Gauer's norm. This part is the Gauer's 2 norm, except for this. And so what you do is, again, let's call this G sub F2 of x H1 H2. So then you again look at expectation of G sub F2 x H1 H2, expectation over y W. So you look at the difference and you show that that is small. So then you can replace this W basically by 1 and then get the Gauer's norm. Yeah, so how do you prove that this is small? Well, you again apply Cauchy-Schwarz by looking at the square root of the absolute value of this. So let's forget the 1/4. And then you look at the because it's also a linear form. So when I apply Cauchy-Schwarz, I can replace G of F2 by G of nu, because each of these is bounded in absolute value by nu plus 1. So, and these linear forms here are not parallel to the linear forms here because of an extra y. So this is G is just a product of some linear forms which all involve an extra variable y. And if I apply Cauchy-Schwarz, or if I want to bound this in absolute value, these will be again some linear forms which do not involve y. And so this will just be a product of linear forms all evaluated on nu with x H1 H2 here and x y H1 H2 there. So when you expand it all out, you will get I don't know, 12 linear forms which are all not parallel to each other, and we'll get that these two products are very close by that condition. Was new.
So pseudo randomness of mu is basically this, that it's product of it.
No, expectation of product of linear forms is very close to 1, which is a generalization of Gauer's norm, right? I mean, saying that Gauer's norm is very close to 1 is a special case of that property, because Gauer's norm has just these 4 linear forms, or 2 to the k linear forms, which look like this. You're not happy with this?
No, okay, so no, I didn't realize before that even this part will use these estimates. So even this part uses this.
Yeah, because there are these different kinds. If there was just one function, just f, then maybe I could have gotten down to Gauer's norm of f directly. But because of these, I need to get rid of these functions which I need to bound by nu. I don't have a bound by 1 on them. Like if they were bounded functions, or if they were just one function, then I could have done this. So in communication complexity, you typically have functions which are between 1 and -1. So all these bounds are just constants. You don't have to deal with a term like this.
Right. Even though the term is like in expectation 1, but if you put it outside, but it's like.
Yeah, in expectation it's 1 certainly, but that's not enough.
Yes.
You have to use that kind of.
So you use even here you use the pseudo randomness.
Yeah. So essentially for this part I need the first condition, and for the other for condition 1 that I wrote there, I'll need the second condition or the correlation bound. Those are the places where they are used. Okay.
And it seems that in one it's more inherent that using it for part 1 is more inherent than for part 2. Or it's
It seems like both the places do need them. I don't know how to think of them without it.
How much simpler does it get in the finite field case?
Well, not much, right? Because this problem is because of the unboundedness of f, right?
I understand, but what do you take even? You know what they take Well, so, I don't know even if it was proved, like if you take
I don't know if they wrote down the proof. I mean, I would believe you can work out similar proof.
Yeah, with the reducible polynomial.
Yeah, but I don't know if it will be much simpler.
Okay.
Okay, now to get to the first condition, so I can just do it there. Okay, so now we are looking at the hypothesis there involves a polynomial of these functions, and instead of a polynomial, let's just think of a monomial or maybe even one multilinear term, and the proof is basically the same thing. So we want to look at this inner product nu minus 1, which is the difference of the pseudorandom measure in the uniform distribution with a product not necessarily of distinct functions, but functions from our class T. So this is a monomial, and we'll just prove it linearly. And we want to show that this is little of 1, so that we can add a lot of them, a bounded number, and still get something which is small. So here you really need the way these functions look. So they are functions which, when multiplied with something else, give you the Gowers norm. And then we need to play around with this a little bit. So,
In the first part, did you use that it's 1 plus little of 1 there, or did you just use that it's bounded?
Bounded was enough.
Bounded was enough.
Well, actually, no. No. 1 plus little of 1 is needed because of this.
Okay.
I need 1. Sorry.
That's strange, because if you multiply the weights by 2, you should still get the same result.
If you multiply the weights by, well, it will not be a pseudorandom measure. I mean, its expectation will not be 1.
No, I'm just saying that for what you wanted, that if the Gauss norm is little of 1, then
well, I could have subtracted instead of 1 some other number if I knew what to subtract. So if I knew that this will be some bounded constant, say 5, then I'll subtract 5 instead of 1 and get the 1. Okay, so what is this? This is expectation over x. And now we have okay, so each of these is a product of a lot of terms, and the proof is basically collecting functions. So let's just do a little bit of jugglery. So let's So let's just reparameterize it in terms of some common variable h, and I'll collect these variables in a nice form. And let's take the expectation over h outside. It doesn't change anything. Now, all you do is use the properties of the norm. So let's write this as so once we have fixed all these values of this capital H, you get one function for each omega, where it is of this form. So for each omega, once you fix capital H, you're looking at a function which is a product of these FIs, and you have an expression of this form. And so this is like Gauer's norm, where I have product over. So this part is like Gauer's norm, where I have a product over omegas of some function, and calculated at x plus h dot omega. To get this extra h is why I did that trick. But these functions are different, and this is what is called the Gauer's Cauchy-Schwarz inequality, is saying that you can write this as a product of the Gauer's norms of the individual functions. So I can just bound it in terms of products of Gauer's norms of these individual functions. So one of these functions, one corresponding to omega equals 0, is nu minus 1, whose Gauer's norm is very small. It's little o of 1, because Gauer's norm is just a bunch of linear terms. Its expectation on nu is 1, and on 1 is also 1. So one of these terms is little o of 1. I just want to show that the rest of the terms are bounded. Right. So comes down to showing that
this Cauchy-Schwarz inequality is what do you prove now? It's just this inequality that you just used.
yeah, so it's the inequality that if you had an expression like Gauer's norm, but every function was different for every omega. You used a different function instead of the same one which you would use when you. Then this is bounded by product of the Gauer's norms of all the functions. So this is but then it just comes down to showing that the product of these norms is small, and these norms, let's just show that one of them is small, and the proof will basically be the same for more. So we just want to show that expectation over h for some omega which is not 0 that's all we want to show now. It's some bounded number, and omega can be any non-zero bit string. Let's just think of something which has one non-zero bit. So what this will do is it will just add one element to x, one non-zero element of h to x, right? Each of them. So this is nothing but so let's think of the first bit of or the first element of h superscript I as ui. So then we are just looking at this is our function, and there is just some one non-zero thing that is being added. And this is nothing but so these are all independent. So this is nothing but this expression, which is norm of a product. Yeah, when you raise to the power 2 to the k. So and yeah, so you raise to the power 2 to the k, you get something of the following form. So expectation of x is I mean, it comes out to be an expression of exactly this form, where you have u1 to ut in this product and hold to the some power. And so this condition exactly says that whatever you get here is bounded. Well, all the way up to k, yeah.
The UI are just general numbers between. Why are they bounded? I mean,
UIs are elements of Zn.
yes.
Yeah.
And
So tau is a function which takes an element of Zn and gives you a real number. So what you will do is you will look at this expectation, you will bound it by something of the following form.
and tau is a function that we think of as a constant.
All of its moments as a constant. So you'll get a bound of the following form.
Which, so for us, we can think of it as basically as, I mean, it's good enough. I mean, as if it was written little of 1 in the right hand side.
Not little of one.
Not big of 1. Big of 1.
Big of 1, yes. So the bound you will get is of something of this form. You will have all the, so you will get all the expressions corresponding to Gauer's norm, but the problem is when you do this right, the expectation will only be over x and not over the h's that comes out in Gauer's norm. They will be outside, and you will get a power of what comes the expectation over x. And that you can bound when you just have expectation over x, you can bound it by this condition. That's all that is used for. So you'll get a bound of something like this, which can again be bounded by the kth moment of tau, some constant times the kth moment, and that is again something which depends only on k and not on n.
Where did the mu came in the
So all these FIs will be bounded by nu plus 1, right? You cannot apply the condition on FIs. So you'll use that.
But is it monotone? They're all positive, yeah.
The FIs?
They're FIs.
No, they are not positive, but you'll bound the absolute values. So you'll break down the expectation in terms of products of absolute values of x.